This video is going to review reasoning with data. It's going to try to integrate some of the different things that we've talked about over the course of the course. Okay, so we have 50 clients participating in job training program A and 50 in job training program B. 60%, 30 of 50 of those in A versus 40%, 20 of 50 of those in B obtain jobs. Our hypothesis pair is non-directional. We select the 0.05 level, that is to say alpha equals 0.05. First thing I like to do in data analysis is get a feel for size of association. The difference in percentages is a great straightforward, if informal measure for so doing. So we have a difference here of 20 percentage points, and that would be categorized as a medium-sized difference. Now, there's no mention in our description above of random sampling. Even though our sampling is non-random, we are going to go ahead and conduct a statistical significance test. So we've got two categorical variables, A versus B, and obtain job versus do not. So our test is going to be a chi-square test, and with this data, the chi-square test yields a p-value of 0.046. This is less than our selected significance level of 0.05, and therefore we reject the null. We conclude that the difference in percentages between A and B is unlikely to be due to chance alone. So another way to think about the difference being unlikely to be due to chance alone is to think instead the difference is likely indeed due to something real. I mean, if it's unlikely to be due to chance, it's likely due to something real. So the question comes up, what is that real thing that is causing our result? And in particular, can we conclude that the something real is the job training program, which is to say A being more effective than B? Now, our description of the situation made no mention of random assignment to groups. Let's go ahead and let's assume that the assignment is non-random. So that being the case, confounding variables cannot be ruled out. The something real causing the difference could be either a confounding variable or the job training program. Basically, because we don't have random assignment and therefore there's the possibility of confounding variables, we just simply don't know which is the better explanation. And so, in essence, we cannot reach a strong causal conclusion. Let's change our example. Let's now presume random assignment to groups. All else stays the same. Random assignment rules out confounding variables. As discussed earlier, our result is indeed statistically significant. Since it's statistically significant, it's due to something real. It's due to something more than chance. Now we've got both statistical significance and we've got random assignment. Because the result is statistically significant, we're confident that it's not due to chance. Because the assignment is random, we're confident that the result is not due to a confounding variable. So basically then, because we've got both statistical significance and random assignment, we can be confident that the result is indeed due to the job training program. The something real is the job training program. So the difference in percentages, 60% versus 40%, we now can conclude that that is indeed due to the treatment intervention. So let's continue to presume that we have our example with the random assignment. So we know that the job training program is the cause of the the difference, so that we know that something about the job training program is explaining our result? Do we know what characteristic of the job training program is causing our result? And the answer is no. We can't be confident about this. Well, it might be ingredient X of the intervention. It might be ingredient Y. Perhaps it's a combination of X and Y. It might even be something so simple as the fact that the persons who deliver program A have better skills than do those who deliver B. Now, our study sample was not drawn from any wider population, or at least the description makes no mention of any such population. So we're going to presume it's a non-probability sample. I mean, we can indeed be confident that our result is not due to chance, and indeed we do know that it's due to some real thing connected with the intervention. But what we can't do is we can't use inferential statistics to generalize our conclusions to any wider population, so that we know that for the 100 people in this study, the intervention made a difference. But we can't statistically generalize to a population of real people and say that the intervention would make a difference for this real wider population. That's because there is no such population. Had we been fortunate enough to be able to select our 100 participants from some wider population, then we would be able to statistically generalize our conclusions to those 1,000 people, say. But in the absence of a real wider population, our conclusions apply to the sample per se. Now, I've been talking as if we know that the result is due to the treatment intervention, but let's step back. The results are unlikely to be due to chance alone, and indeed we can be more than 95% confident that the results aren't due to chance alone. I mean, the p-value was 0.046, and we can actually carry out a calculation. We can be 95.4% confident that the result is not due to chance alone. But viewed differently, there is in effect a 4.6 chance that the study result is due to chance alone. So I've been talking as if we know the result isn't due to chance, but really I should have been saying we can be confident that the result isn't due to chance. Statistical conclusions are always going to be probabilistic conclusions. We are never going to know for sure. I mean, we are never going to know with 100% certainty. The best we're going to be able to do is to be very confident. Let's toss another twist on our results. Let's say that the results are not statistically significant. In other words, that p is greater than 0.05. Here, we can't rule out chance as a plausible explanation for the difference in percentages. In other words, the results may well be due to chance alone. Now, chance alone is the simplest possible explanation. So if the results aren't statistically significant, they may be due to this very simplest possible explanation, chance. In such a situation, science doesn't permit us to think about real factors that may or may not also be involved. If chance alone is sufficient, that's basically the end of our thinking. We don't have really a permission to do further thinking. We don't have solid grounds to think that real factors are also involved. So if the results may simply be due to chance, in essence, it makes no difference whether or not we have random assignment. We have no solid data that there's a real difference between, in this example, the two programs, and as such we presume the results are simply due to chance, and the question of whether the result is due to a confounding variable or to the real effects of the treatment, that question wouldn't even come up if our result was not statistically significant. And so here you see this notion of science wanting you to go forward with the simplest possible explanation. If chance is a plausible cause, we're not permitted to consider real factors. So, in our changed example, p is greater than 0.05, we fail to reject the null. So in a situation like this, be sure not to reach these conclusions. They don't follow. The null is likely true. We can be confident that the null is true. It is likely that the results are due to chance alone. The null is true. None of these conclusions are valid conclusions. When you fail to reject the null, all that we know is that we don't have strong enough, we don't have sufficient evidence to reject it. So therefore, we retain it. We fail to reject it. We don't know that it's true, we just simply don't have strong reason to think otherwise. Let's put one final twist on our results. Let's presume that we carry out this study with much smaller sample sizes. Not with 50 in each group, but rather with 10 in each group. And we'll keep the percentages the same. Now in this situation, the chi-square test results are nowhere near to being significant. P now equals 0.371. In this situation, we have very small sample size. And that being so, our statistical power is likely very low. In this situation, it's almost assuredly the case that we don't have a genuine opportunity to reject the null. So I'll simply read the conclusion that I think expresses best the state of affairs in this final example. Because we did not have a genuine opportunity to reject the null, we can't make an informed statement regarding which hypothesis, the null or the alternative, provides the better explanation for the study result. With very low power, one fails to reject the null almost by default.